Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So if you want to put human beings on Mars, your absolute biggest enemy isn't the radiation.
Right.
And it isn't the freezing temperatures either. It is weight. I mean, launching just the rocket fuel needed for a return trip back to Earth, well, that would require a launch vehicle so impossibly massive that it basically bankrupts the entire mission before it even leaves the launch pad.
Oh, absolutely. It's just a non-starter, financially and physically.
Exact. So space agencies have had to come up with a radically different plan, which is do not bring the return fuel at all. Make it there. But to make fuel on Mars, you need to find massive, accessible deposits of subsurface water ice, and you need to find them fast.
Very fast. The clock is ticking on those 2030s deadlines.
Yeah, which brings us to this frankly staggering announcement from the March 2026 Ignition event, a mission called Skyfall. I mean, just the name sounds like a movie.
It really does. It has a very cinematic ring to it.
It does. And the plan is wild. They want to launch a nuclear-powered spacecraft, fly it to Mars, and instead of, carefully lowering a rover to the ground, this ship will plunge into the Martian atmosphere and violently eject a squadron of 6 autonomous helicopters midair.
Just drop them right out of the sky.
Right. They will free fall at supersonic speeds, deploy their rotors, catch themselves before hitting the dirt, and scatter across the planet to hunt for ice. I mean, it sounds totally reckless when you describe it like that.
Oh, I know. Dropping a multi-billion-dollar fleet out of the sky mid-entry seems to violate, basically every safety protocol we've spent the last 60 years developing for planetary landings.
Yeah, that's what I was thinking.
But when you look at the brutal mathematics of the 2030s human landing deadlines, the conventional methods of exploration like slowly rolling a single car-sized rover across the dunes are statistically guaranteed to fail.
Because they're just too slow.
Exactly. We do not have the time to survey an entire planet on wheels. Skyfall is the forcing function here. It is a necessary, albeit incredibly aggressive, architectural shift from crawling to swarming.
Wow. Okay, I am still trying to wrap my head around the visual of mid-air deployment at Mach speeds. But before we get into the aerodynamics of a falling swarm, I want to trace how we got here.
Sure, because this didn't happen in a vacuum.
Right, NASA didn't just wake up in 2026 and decide to build nuclear paratrooper drones. This entire mission architecture rests on the shoulders of what I used to think of as a neat little science project, the Ingenuity Mars helicopter.
Oh, calling Ingenuity a science project severely understates the aerodynamic nightmare of its creation.
Really? A nightmare?
Oh, yeah. To understand why Skyfall is possible, you really have to understand why Ingenuity shouldn't have been. I mean, the atmosphere on Mars is mostly carbon dioxide, and it is thin.
How thin are we talking?
It sits at about 1% of the density of Earth's atmosphere at sea level.
Okay, so if I'm an engineer tasked with flying in air that thin, my immediate instinct is to just, scale up, like make the rotor blades vastly longer and wider to catch more of whatever sparse air is actually there. It seems like a simple geometry problem to me.
You'd think so, right? That's the logical first step. But increasing the blade length runs you face first into a physical wall, which is the speed of sound.
Wait, the speed of sound is different on Mars.
Yes. Mars is incredibly cold, and sound travels through that thin CO2 atmosphere much slower than it does on Earth. It's about 240 meters per second compared to our 340.
Oh, wow. I had no idea.
Yeah, so if you build massive rotor blades and spin them fast enough to generate lift, the tips of those long blades will easily exceed the Martian speed of sound. And the moment that happens, you generate destructive shock waves.
Like a sonic boom hitting the blade itself.
Essentially, yes. The air basically turns into a brick wall of drag, the blade loses its lifting capability, and the helicopter just tears itself apart.
Yikes. So you literally cannot just build huge blades.
Exactly. Instead, the team at JPL had to keep the blades relatively short, about 1.2 meters across, and spin them at an agonizingly precise speed. We're talking around 2,400 to 2,500 revolutions per minute.
That sounds incredibly fast.
It is. That is roughly 5 times faster than a standard passenger helicopter on Earth. So they had to engineer these blades out of carbon fiber foam cores just to be stiff enough not to bend under those extreme rotational forces.
While keeping the weight down, I assume.
Right. keeping the entire vehicle under 2 kilograms.
Man, that makes the reality of what Ingenuity accomplished terrifying in retrospect. I mean, it was designed to fly maybe 5 times over 30 days. It was just a tech demo to prove powered flight was even possible.
Just a proof of concept, yeah.
Instead, it survived the freezing Martian winter, which, by the way, it completely lacked the heaters for, and it flew 72 times over 3 years. It absolutely smashed its targets, outperforming its flight target by more than 14 times and its longevity target by 32 times.
It's an unprecedented engineering triumph.
It is, but I still see a massive leap in logic here. I understand Ingenuity was a triumph. It's the right flyer of Mars. But it was still a tiny scout that relied entirely on the Perseverance rover acting as its communication base station.
That's true. It couldn't talk to Earth directly.
Right. So bounding from that localized success to betting the entire site selection process for human habitation on an unproven fleet of autonomous heavy-duty helicopters, that seems incredibly precarious. I mean, we know how to build rovers. We have decades of experience with wheels. Why not just send 6 rovers?
Well, because wheels are an illusion of safety. If you look at the actual operational history of our Martian rovers, they are agonizingly slow, and they are highly vulnerable to the terrain.
I mean, they do look pretty slow in the videos.
It's worse than it looks. Because of the light time delay in communicating with Earth, which ranges from 4 to 24 minutes depending on orbital alignments, you cannot drive a rover manually.
So no one is sitting there with a joystick?
No, definitely not. A human cannot use a joystick to steer around a rock, because by the time the video feed of the rock reaches Earth, well, the rover has already crashed into it 20 minutes ago.
That makes sense. It's already in the past.
Right. So every single movement of a rover is plotted in advance. The rover takes photos, beams them to Earth. Engineers spend hours building a 3D terrain mesh, simulating a path, and then they beam up a command that says, drive forward 3 meters and stop.
3 meters, that's it.
A fantastic day of driving for a rover is perhaps 100 meters.
And the terrain isn't exactly a paved highway either. I remember the Spirit rover breaking through a crust of soil in 2009. It just sank into a hidden sand trap and became permanently bogged down.
We lost the whole vehicle right there.
Yeah, and Curiosity's aluminum wheels looked like they had been chewed through by metal shears after just a few years of driving over those sharp wind-carved rocks.
And that is the core issue. Rovers are crawling blind through a minefield of geological hazards. If your objective is to map thousands of square kilometers of terrain to find a massive, pure, subsurface ice sheet.
Right, because we need the ice.
Exactly, an ice sheet that is also situated near flat ground suitable for a human landing craft. A rover will take half a century to do that.
Half a century. And we want to land humans in the 2030s, so the math just doesn't work.
It doesn't. Helicopters completely bypass the terrain problem. They fly over the sand traps that killed Spirit. They soar over the jagged rocks that shredded Curiosity's wheels. They can drop into a massive crater, map the stratigraphy of the steep walls, and fly back out in an afternoon.
So they're just on another level entirely in terms of speed.
What takes a rover 6 months to navigate? An aerial asset surveys in 4 hours. So NASA didn't abandon rovers because they wanted a flashier technology. They abandoned them because the mathematics of the 2030s human arrival deadline dictate that aerial swarms are the only physical way to survey enough ground in time.
Okay, that reframes the entire timeline for me. It is an issue of scale and speed, but scaling up brings us to a brutal logistical bottleneck. If we are moving from a single 2-kilogram drone to a fleet of 6 advanced heavy payload helicopters, the mass we need to send to Mars increases exponentially.
Drastically.
And we need them there incredibly fast to do the prospecting before astronauts start prepping for launch. So traditional chemical rockets, burning liquid fuel and oxidizer, they have hard limits.
Very hard limits when it comes to mass.
Yeah, I'm looking at the architecture for the Skyfall carrier spacecraft, and NASA isn't using chemical propulsion for the main transit. They're using the SR-1 Freedom, a spacecraft powered by a 20-kilowatt nuclear electric propulsion system.
Yes. This is where Skyfall graduates from a clever robotic mission to a foundational shift in interplanetary infrastructure. The SR-1 Freedom represents the death of the traditional rocket equation for deep space transit.
The rocket equation, break that down for me.
So for decades, every probe we have sent to Mars has relied on the same fundamental mechanism. You burn a massive amount of chemical propellant for a few minutes to break Earth's orbit, and then you just coast through the vacuum of space for 7 to 9 months until you hit Mars.
It's like pedaling a bicycle as hard as humanly possible for the first 10 seconds of a race, getting up to your maximum speed, and then entirely taking your feet off the pedals and just coasting for the next 6 months.
That's a perfect way to think about it.
Hoping you calculated the trajectory perfectly to cross the finish line, all the energy is basically dumped at the very beginning.
That is a highly accurate way to visualize it. And the problem with chemical propulsion is that fuel is incredibly heavy.
Right.
If you want to push a heavier payload like 6 advanced helicopters, you need more fuel to push it. But now your rocket is heavier because of that extra fuel, which means you need to add more fuel to push the fuel you just added.
It's a trap.
It is. This exponential punishment is known as the Tsiolkovsky rocket equation. It is a vicious cycle of diminishing returns that makes chemical rockets horribly inefficient for massive payloads.
So how does nuclear electric propulsion, or NEP, bypass this?
It breaks that cycle entirely. The SR-1 Freedom uses a small nuclear fission reactor. The reactor itself does not generate thrust. Instead, the controlled splitting of uranium atoms generates a massive amount of heat, which is converted into a constant 20-kilowatt supply of electrical power.
Okay, so it's a flying power plant.
Exactly. And that electricity is fed into an ion thruster. The thruster takes an inert gas, usually xenon, and uses the electricity to bombard the xenon atoms, stripping away electrons to create positively charged ions.
I see.
Then, using an intense magnetic field, the thruster accelerates those ions out the back of the spacecraft at velocities approaching 90,000 miles per hour.
90,000 miles per hour. Wow. So instead of a violent explosion of chemical fire, an ion drive is essentially shooting an invisible beam of charged particles out the back.
That's exactly what it's doing.
But I know that the actual physical force of that thrust is incredibly weak. I've read it compared to the weight of a piece of paper resting on your hand. How does a force that weak move a massive spacecraft carrying 6 heavy helicopters all the way to Mars?
The secret is time and efficiency. You are correct that the instantaneous thrust is minuscule. But going back to your bicycle analogy, an ion drive is like having a small electric motor that never ever stops pushing.
So it's constant acceleration.
Yes. Because the xenon ions are expelled at such extreme velocities, the engine is vastly more fuel efficient than a chemical rocket. In aerospace terminology, it has an incredibly high specific impulse.
Specific impulse, got it.
In the vacuum of space, there is no friction. So that tiny continuous push from the ion engine accumulates day after day, week after week. The spacecraft slowly but relentlessly accelerates, eventually achieving transit speeds that completely dwarf what a coasting chemical rocket can manage.
Okay, if the physics of specific impulse make NEP vastly superior for heavy payloads, I have to ask the obvious question. We have known about nuclear fission since the 1930s. We have known about ion propulsion for decades. Why is this just now flying on the SR-1 Freedom? Why didn't we build this in the 1990s?
Well, it comes down to the intersection of political risk and technological necessity.
Politics.
Always.
Yeah.
For decades, NEP was relegated to theoretical paper studies. Why? Because chemical rockets were good enough to send tiny, lightweight robotic probes to Mars.
And no one wants to launch a reactor if they don't have to.
Precisely. When a chemical rocket is good enough, no space agency wants to tackle the regulatory nightmare of launching a live nuclear reactor into Earth orbit. The safety reviews are monumental.
But something changed.
The payload changed. As NASA Administrator Jared Isaacman recently outlined, we have hit the physical limits of good enough. You simply cannot lay the infrastructure for a multiplanetary economy using chemical rockets.
Because you can't lift the habitats and the fleets?
Exactly. The mass penalties are simply too high to move human-rated landers, habitats, and heavy reconnaissance fleets like Skyfall. Skyfall is the forcing function. The national space policy objectives have finally demanded a payload mass that chemical rockets cannot efficiently deliver. The need for the fleet necessitated the reactor.
Okay, so the SR-1 Freedom solves the transit bottleneck. We break the tyranny of the rocket equation using fission and magnetic fields, and we arrive at Mars with our heavy payload. But this is where my anxiety about this mission architecture spikes.
I think I know where you're going with this.
The transit is solved, sure, but the landing method, the Skyfall maneuver, seems fundamentally unhinged. I mean, let's contrast this with how we landed Perseverance.
The sky crane.
Right, the sky crane.
Right.
That was a system where the spacecraft entered the atmosphere, a massive supersonic parachute deployed to slow it down. Then the heat shield dropped off. Then the rover essentially dropped out of the back shell, attached to a jetpack.
It was brilliant engineering.
It was. The jetpack fired its thrusters to halt their descent, and while hovering in midair, it gently lowered the rover down to the dirt on nylon cords.
Yes.
Once the wheels touched down, the cords were severed, and the jetpack flew away to crash at a safe distance. It was an incredibly complex, delicate ballet on a tightrope, like lowering a car on a string.
It really was a marvel.
But Skyfall abandons all of that. You have the aeroshell hitting the atmosphere, taking the thermal load of thousands of degrees of plasma, and then miles above the surface, traveling at Mach speeds, the shell just pops open and ejects 6 helicopters into freefall, like paratroopers jumping out of a C-130.
It is a very dramatic shift.
If you are dropping these things from a skyscraper equivalent altitude at supersonic speeds into unpredictable Martian winds without a parachute stabilizing them all the way to the ground, I mean, how is that not a recipe for total catastrophic failure? If the atmosphere is so thin, how do they even catch themselves before hitting the ground? What if half of them crash on day one?
You are looking at the Skyfall maneuver through the lens of traditional risk management, which prioritizes the preservation of a single, highly controlled asset.
I guess I am. I don't want the billion-dollar drone to crash.
Understandable. But let's analyze the sky crane you just described. It is a brilliant piece of engineering, but it is the ultimate single point of failure architecture.
Meaning if one thing breaks, it's over.
Exactly. If the supersonic parachute tears upon deployment, the mission is over. If the radar altimeter on the jetpack glitches and miscalculates the distance to the ground, the mission is over. If one explosive bolt fails to sever the nylon cord, the mission is over.
Oh, wow. Yeah, that's a lot of things that have to go perfectly right.
Every single step must execute flawlessly, or you're left with a multi-billion-dollar crater. The mid-air deployment of Skyfall introduces a fundamentally different risk model: statistical survivability through distributed architecture.
So you're saying they expect some of them to crash?
They are mathematically prepared for it. Let's walk through the physics of the drop. The SR-1 carrier vehicle hits the atmosphere. The heat shield absorbs the kinetic energy, turning it into plasma, and slows the vehicle down significantly, though it is still traveling very fast.
Right.
At a calculated altitude, the aeroshell opens. The 6 helicopters are deployed. Now, they're not entirely at the mercy of the wind immediately. Their chassis are aerodynamically designed to passively orient themselves as they fall, ensuring their center of mass points downward.
Like a shuttlecock.
Exactly like a shuttlecock. As they enter freefall, the onboard flight computers boot up in milliseconds. And they do not just blindly turn on their engines, they initiate a state of auto-rotation.
Auto-rotation? What is that?
The upward rush of air through the unpowered blades causes them to spin, which stabilizes the craft aerodynamically. Once stable and oriented, the motors engage, applying massive torque to the blades to violently arrest their vertical velocity.
That sounds like dropping a drone from a skyscraper, expecting it to power on, orient its cameras, and hit the brakes 10 feet before the pavement, but doing it in a near vacuum.
It is intensely violent. There will be massive aerodynamic loads on the rotors, but consider the math of the distributed swarm. If you send one rover on a sky crane and a sensor fails, your mission is a 100% failure.
Yeah.
You have 0 assets.
Yeah, you've lost everything.
But if you eject 6 helicopters midair and the crosswinds are worse than modeled, or a deployment mechanism jams, and 2 of those helicopters crash into the Martian surface.
You still have 4 left.
Exactly. You still have a 66% mission survival rate. You have 4 fully operational advanced aerial assets spreading out across parallel geographic zones.
So the goal isn't necessarily landing safely in one spot. The goal is landing widely. Because if you safely lowered a platform with 6 helicopters on it, they would all have to launch from the exact same starting point, basically wasting fuel just to get away from each other.
Exactly. The mid-air deployment acts as a multiplier for their operational range. You scatter them across a 500-kilometer zone instantly, mitigating the single point of failure risk and simultaneously initiating reconnaissance in 6 distinct geological regions.
That is wild, but it makes so much sense. Okay, let's follow the timeline forward. The drop occurs. Let's assume the statistics hold up, and at least 4 or 5 of these mechanical paratroopers successfully auto-rotate, fire their motors, and touch down safely in the dust.
Fingers crossed.
Right. They're sitting on the Martian surface. Their hybrid solar power systems boot up. What exactly is the hardware capable of? Because I know JPL and AeroVironment didn't just build 6 clones of Ingenuity.
Definitely not.
Ingenuity had a couple of commercial cameras and a smartphone processor. These Skyfall units have a very specific job. Find the ice so we can make the fuel. They're basically autonomous flying geologists with X-ray vision.
That's a great way to put it. The hardware evolution is staggering. You have to remember, the Martian environment is actively hostile to moving parts. The dust is not like beach sand. It is incredibly fine, highly abrasive, and statically charged.
It just sticks to everything.
It clings to everything, works its way into bearings, and severely degrades solar panel efficiency. So the Skyfall units are heavily ruggedized, completely sealing their articulation joints. But their true power lies in their scientific payloads.
Tell me about the payloads.
They carry high-resolution optical and thermal imaging to map surface hazards, like jagged rocks or treacherous slopes that could tip over a future human habitat module. But the absolute crown jewel of the fleet is the ground-penetrating radar.
Let's dig into that radar, because looking at surface pictures only tells you where not to land, doesn't tell you where the resources are.
Exactly.
Mars looks bone dry on the surface because the atmospheric pressure is so low that liquid water would boil away instantly, and exposed ice sublimates directly into gas.
Yes, it skips the liquid phase entirely.
Right. We know the ice is trapped underground. But how does a flying drone actually see it?
Ground-penetrating radar, or GPR, exploits the way different materials interact with electromagnetic waves. As the helicopter flies low over the surface, the GPR payload pulses radio waves down into the dirt.
Okay.
When those radio waves travel through homogeneous Martian regolith, which is just dry dirt and rock, they move at a relatively constant speed.
Yeah.
But when those waves hit a boundary between different materials, like a layer of rock sitting on top of a massive sheet of water ice,
Something changes.
yes, the change in the material's dielectric permittivity causes a portion of that radio energy to bounce back up to the helicopter's receiver.
Like an echo.
Precisely. By measuring the exact time it takes for the echo to return and the strength of that echo, the flight computer can build a highly precise three-dimensional topological map of what exists beneath the surface.
Wow.
It can determine exactly how deep the ice is buried, how thick the vein is, and even infer its purity.
And this data is the literal foundation of in situ resource utilization, or ISRU. We throw that acronym around a lot, but the chemistry of it is fascinating.
It really is.
If these helicopters find a massive sheet of subsurface ice, the 2030s human mission will land a robotic chemical plant on top of it. That plant will drill down, melt the ice, and pump up liquid water.
That's step one.
From there, it is basic chemistry. You run an electrical current through the H2O, a process called electrolysis, which splits the water into hydrogen gas and oxygen gas. The oxygen is compressed and stored, both for astronauts to breathe and to act as the oxidizer for the rocket engine.
Perfect. But we're still missing half of the rocket propellant.
Right, you still need fuel, and this is where the Martian atmosphere actually helps us. It is 95% carbon dioxide. If you take that CO2 from the air and combine it with the hydrogen you just split from the water, you can run them through a Sabatier reactor at high temperatures.
The Sabatier reactor.
Yes, and that reaction produces water, which you cycle back into the system, and methane. Liquid methane is the exact rocket fuel that many next-generation engines use.
The chemistry is well understood and highly reliable. The entire ISRU concept is sound. But it all hinges on one absolute prerequisite, which is that you must build the chemical plant directly on top of the ice.
You can't just drive over to it later.
No, you cannot land a heavy drilling rig, realize the ice is actually 5 kilometers away, and just drive the rig over. The mass is too great. Skyfall's radar grid searches are the only way to gain the absolute certainty required to lock in those coordinates before we send the plant.
Which brings us back to the most mind-bending logistical aspect of this entire operation. With the communication delay between Earth and Mars, there is no one flying these things with a joystick.
Didn't want it all.
We established earlier that rovers are paralyzed by the light time delay. If a Skyfall helicopter is blasting over a canyon at 50 miles an hour, scanning for ice, and a massive rock wall suddenly looms in its path, it cannot radio Earth for instructions.
It would be a bug on a windshield before the signal even left Mars.
Exactly. By the time the video feed reaches Earth, 20 minutes have passed and the drone is already shattered against the cliff. Furthermore, we do not have a constellation of GPS satellites orbiting Mars.
That's a huge factor people forget.
Right. On Earth, drones know their precise altitude, velocity, and location because they are constantly pinging atomic clocks on satellites. On Mars, they are flying totally blind regarding external positioning. How do 6 independent helicopters coordinate, avoid hazards, and relay data without constant babysitting from mission control?
The solution is the deployment of advanced swarm artificial intelligence and a technology called terrain relative navigation. It heavily utilizes SLAM algorithms, simultaneous localization and mapping.
Slam. Okay, how does that work?
Because they have no GPS, the helicopters must rely entirely on their own internal sensors and cameras to understand their position in space. As the helicopter flies, a downward-facing navigation camera takes dozens of high-resolution photos per second.
Just constantly snapping pictures of the ground.
Right. And the onboard AI instantly analyzes these photos, identifying specific visual features, like the edge of a crater, a uniquely shaped boulder, or a ripple in a sand dune. By comparing how far and in what direction those specific features move from one frame to the next, the AI calculates its own exact velocity and direction of travel. This is optical navigation.
Oh, that's brilliant. It's using the ground as its own tracking pad.
Exactly. And at the same time, forward-facing LiDAR and stereoscopic cameras are building a real-time 3D mesh of the environment ahead. If the AI detects that a cliff wall intersects its projected flight path, it doesn't need to ask Earth for permission to turn.
It just does it.
Yes. The hazard avoidance algorithms autonomously calculate a new trajectory, bank the rotors, and steer the craft around the obstacle, all in fractions of a second.
That is incredible. They are essentially building the map of the world and their place within it, frame by frame as they fly. But they aren't just flying around randomly, right? To cover maximum ground, they have to coordinate.
Precisely. They do not operate in a vacuum. They communicate via high-frequency radio links to the various Mars orbiters passing overhead. When an orbiter is in line of sight, a helicopter blasts its accumulated radar data, visual maps, and positional coordinates up to the satellite, which relays it to Earth.
Near real-time data relay.
Yes. But they also share broad positional data with each other. This creates a parallel exploration model. Let's say Helicopter 1 might be mapping the northern edge of a promising basin, and it registers a high-density ice deposit.
Okay.
Helicopter 2, operating 10 kilometers away, receives an updated priority directive based on that find, and autonomously adjusts its flight path to map the southern boundary of that same basin. This way, they work together to determine the total volume of the ice sheet.
Without humans telling them to do that.
Exactly. Yeah. Mission control on Earth is not flying these vehicles. They are simply uploading high-level strategic objectives. They beam a command saying, "Grid search Sector 4 for high permittivity radar returns," and the swarm AI breaks that command down into tactical flight paths, delegates the terrain among the surviving units, and executes the search autonomously.
Wow, so we have a mission architecture that breaks the rocket equation with a nuclear ion drive, fundamentally changes landing risk modeling with supersonic mid-air deployment, and solves the communication delay with autonomous optical navigating AI swarms. On a technical level, it is a masterpiece of logic.
It truly is.
But, and I hate to do this, let's initiate a reality check.
Okay, lay it on me.
We have to look at the timeline NASA's proposing for this and the massive risks involved in actually getting it off the launch pad. AeroVironment publicly unveiled the mature Skyfall concept in July 2025. NASA formally announced adoption in March 2026. The target launch window is December 2028.
That is a very tight turnaround.
Very tight. And for context, launching to Mars is not like launching to the moon. You cannot go whenever you want. Earth and Mars orbit the sun at different speeds. To send a spacecraft efficiently, you have to use a home and transfer orbit, which requires Earth and Mars to align perfectly.
Right, and that alignment only happens roughly every 26 months.
Exactly. If Skyfall misses that December 2028 launch window, the spacecraft is grounded until early 2031. If it launches in 2031, it doesn't arrive until late 2031 or 2032. That completely destroys the timeline for analyzing the radar data, selecting the site, and building the ISRU plant before the first human crews are scheduled to depart in the late 2030s.
It creates a domino effect of delays.
So going from mission adoption in 2026 to launching a nuclear reactor and 6 autonomous helicopters in 2028 is practically light speed in aerospace terms. Historically, flagship missions like the Perseverance rover took nearly a decade to develop. A 2026 announcement for a 2028 launch utilizing space reactors and mid-air drops. That timeline is aggressively fast. Is this growing model of public-private partnerships, like the one with AeroVironment, the secret sauce making this even theoretically possible?
Yes, the acceleration is entirely dependent on a paradigm shift in how NASA procures and integrates technology. For the past 50 years, the agency relied almost exclusively on bespoke engineering.
Building everything from scratch.
Right. If they needed a flight computer, they designed a custom radiation-hardened microchip from scratch, built it in a clean room, and tested it for 5 years. That process ensures reliability, but it guarantees slow development and astronomical costs.
Which they just don't have time for now.
Exactly. What the public-private partnership with companies like AeroVironment proves is the viability of commercial off-the-shelf, or COTS, components. Ingenuity was the ultimate proof of concept for this.
How so?
Its primary processor was not a billion-dollar bespoke JPL chip. It was a Qualcomm Snapdragon processor, fundamentally similar to the brain of a high-end consumer smartphone.
Wait, really? A smartphone chip flew on Mars?
Yes, because AeroVironment had already spent years maturing the swarm logic and rotor mechanics using commercially adapted technologies. By 2025, NASA did not have to start from zero.
It makes a huge difference.
It does. NASA's role shifted from inventing everything to integrating and funding. NASA provides the SR-1 Freedom Carrier vehicle, handles the interplanetary trajectory, and manages the deep space communication network. AeroVironment delivers the finished helicopter fleet. This division of labor is the only mathematical way they hit the 2028 window.
Okay, I see how that speeds things up. But relying on commercial tech and rushing a timeline introduces terrifying risks. Let's look critically at the failure points of this mission, because any one of them could derail the 2030s human exploration mandate entirely.
The hurdles are indeed severe, and I'd say the absolute highest hurdle is nuclear launch certification.
Yeah, putting a reactor on a rocket over Florida.
Exactly. We have launched nuclear material into space before. The Perseverance and Curiosity rovers both utilize multi-mission radioisotope thermoelectric generators, or MMRTGs.
Right, but those aren't full reactors.
No, an RTG is entirely passive. It is simply a chunk of decaying plutonium-238 that gets naturally hot, and thermocouples turn that heat into a tiny trickle of electricity, about 110 watts.
Barely enough to power a light bulb.
Exactly. The SR-1 Freedom is completely different. It is an active nuclear fission reactor generating 20,000 watts.
That's a whole different ballgame.
Placing an active reactor on top of a chemical rocket and launching it from the Florida coast requires navigating the most stringent, unforgiving safety reviews in the history of the federal government.
I can't even imagine the paperwork.
It's staggering. The engineering required to guarantee that the reactor core cannot shatter and scatter radioactive material over the ocean in the event of a launch pad explosion is immensely difficult. Proving that to the regulatory agencies by 2028 is a monumental bureaucratic and engineering challenge.
Oh, and even if they get the launch certification and the SR-1 successfully uses its ion drive to reach Mars, well, we are back to the mid-air drop.
Ah, yes, the drop.
You explained the logic of distributed risk earlier, and it makes sense statistically. But aerodynamic theory in a computer simulation is very different from actually plunging through the Martian atmosphere.
Very true.
The atmospheric density on Mars fluctuates wildly based on the season and the amount of dust in the air. If the carrier vehicle hits an unexpected low-density pocket of air during entry, the aeroshell might open at the wrong altitude.
That's a very real concern.
If they are dropped too high, they run out of battery before reaching the ground. If they're dropped too low, the autorotation fails to arrest their momentum in time, and all 6 hit the ground at terminal velocity.
The aerodynamic uncertainty during the descent vector is absolutely the highest probability failure point for the physical hardware. There's just no way around that risk.
And if they survive the landing, we face the third major risk, which is environmental degradation. Mars is a brutally hostile environment. The dust storms are not just localized events. Mars frequently experiences global dust storms that can obscure the sun for months.
We saw what that did to the Opportunity rover.
Exactly. This abrasive dust coats solar panels, choking off their power supply. It works its way into the carbon fiber rotor bearings. Even with ruggedized joints and hybrid power management, the environment is actively degrading the hardware every single second.
It's a race against the elements from the moment they touch down.
And yet, despite the regulatory nightmare of the nuclear launch, the terrifying ballistics of a mid-air Mach-speed deployment, and the relentless assault of Martian dust, space agencies are pushing all their chips to the center of the table on this specific architecture.
They have to.
It tells you everything you need to know about how desperate the need for subsurface ice is. The risk of the mission failing is massively outweighed by the absolute necessity of the data it provides.
Right.
We cannot guess where to land humans. We cannot send an expeditionary crew millions of miles, land them in a dusty basin, and just hope their drills hit water.
Exactly. The margin for error on a human mission is zero. Skyfall is the mechanism that removes the multi-billion-dollar guesswork from planetary colonization. The commercialization of Ingenuity's avionics makes it affordable, while the mission as a whole answers the most critical question in space exploration right now. Where exactly is the safest, most resource-rich place for humanity's first Martian outpost? But beyond the immediate utility of finding ice, we must recognize what Skyfall represents on a macro level. If this mission succeeds, it validates the infrastructure required for a permanent spacefaring civilization.
It proves the whole system works.
It proves that we can safely launch and utilize high-power fission reactors for deep space transit, drastically cutting travel times. It proves we can utilize autonomous AI swarms to rapidly prospect alien environments without micromanagement from Earth. It graduates humanity from sending delicate, isolated science experiments to deploying robust, industrial-scale exploration fleets.
We are quite literally watching the foundational infrastructure of a multi-planetary economy being engineered and tested in real time. To bring the scope of this all together, it is incredible to trace the lineage.
It's breathtaking.
We went from Ingenuity, a tiny 2-kilogram drone built to answer the simple question of whether air could support flight on another world, to the SR-1 Freedom, a nuclear-powered ion ship crossing the void, poised to violently tear away the safety nets of parachutes and sky cranes.
A huge leap.
It will scatter a swarm of heavily armored, autonomous, radar-equipped AI scouts into the freezing winds of the Red Planet to hunt for the chemical components of rocket fuel. It is a paradigm shift of the highest order.
It is the definitive bridge. The transition from the era of robotic curiosity to the era of human habitation.
I want to leave you with a visual to hold on to as we track the progress of this massive engineering endeavor over the next few years. Fast forward a decade. Imagine the 2030s. The first human astronauts have made the transit.
The culmination of all this work.
Right. Their landing craft descends flawlessly, touching down on a flat, geologically stable plane that was scouted and verified years prior. They step out of the airlock, their boots crunching into the red, iron-rich dirt.
Making history.
The water they drink inside their habitat, the oxygen they breathe, and the tens of thousands of pounds of liquid methane fuel sitting in their ascent vehicle waiting to take them home. All of it was manufactured by a robotic chemical plant, built exactly on the coordinates mapped by the ground-penetrating radar of a machine that fell from the sky.
It gives you chills.
Imagine those future explorers perhaps taking a rover out for a surface survey, cresting a massive red dune. And there, sitting silently in the sand, its carbon fiber blades coated in a thin layer of dust, is one of the Skyfall helicopters. Its battery long dead, its mission perfectly executed. A small, historic monument to the mechanical swarm that survived the supersonic drop, mapped the underworld, and paved the precise way for humanity to finally arrive.
What a sight that would be.
It really makes you wonder, centuries from now, when we finally build the first great museum on Mars, which of those 6 machines will they put in the center hall?